Right, so I think I've gone live now, and I'll probably post the link onto Twitter as well. So let's actually get the link. So let's just hit refresh here. I'm just refreshing the page because it's got the coding sessions on it. So I've got a live session. So I can presumably click in there and then get shareable link. And I will post the link here. Retweet, quote a retweet. Here is the link. So basically, this session's live on YouTube, and really what you're going to see is kind of like the hard way of coding rather than the standard videos that sort of like show you everything and put it all into a script and it all works because it was pre-done and pre-checked, and that's just not how coding works. And the reason why I'm particularly doing this is because I had a project that was open and I did a YouTube video on it already. So I'll try not to cover the extra ground, but basically, hit clear at the bottom here. But basically, I created an n-body simulation of galaxy mergers. Well, I say not even galaxy mergers, but basically an n-body simulation, which is a whole bunch of particles, effectively, or planets you could imagine as, and they're acted on by the force of gravity, and they should move in a certain way. And I created that on my laptop over the weekend, and that worked really nicely. And then I went to run it on this 50-inch widescreen monitor, and it looks like this. F5, if I can run it. So there you go. It kind of like looks like that, which is really, really annoying. Now, I might make that loop just run for a little bit longer, just so that we can see again. But basically, the issue is that it's got those horizontal white lines in there that were rather, they shouldn't be there. And I don't know where they came from. I can only assume that it's some sort of rendering between a smaller screen and a larger screen because I'm using exactly the same code and so forth. But basically, what I'm going to attempt to do, and what I attempted to do in the last video, is to troubleshoot, and effectively I'm going to have to rebuild the code, create like a minimum reproducible example, as it was called, until I either reproduce the lines or the lines don't appear again there. So I'm just going to scroll down on the code because it was somewhere here. I just set it to stop at 250, but let's just make that 500 so it'll run for a little bit extra. That's just so that it switches itself off so I don't have to press a little cross at the top. And also, I was just wondering if I could add a bit more gravity in here, but what we see here now is if I do F5 again, it launches like not in this screen, but there we go. You sort of like see the particles, and this is that horizontal line that I don't want there, all of those horizontal lines. So, and then it sort of disappears at loop number 500 over there. So one thing that I want to do, just quickly if I can, is I might set gravity, but I wonder even if that's working. Somewhere in there I've got a force of gravity. Let me actually have a look. G M. Okay, no, the results, there we go, found it. I was just looking for, because I've got the change of velocity here, and basically the change in velocity according to force equals mass times acceleration, but in our case we've got this gravitational constant, which would be actually this really, really tiny number times the mass, and that's the mass of the entire system, and then the other mass, which is the mass of any particular particle in the system, and then r squared. So divided by r squared, well, 1 over inversely proportional to the square of the distance between the particle and its center of mass. And I should probably draw that out, really, I guess. So I've got this thing here, but I'm going to do a new because it's not this. By the way, this is how the pygame screen looks. So we start, because sometimes it's confusing, but we basically start here. Oops, I didn't mean to do that. I'll do an undo there. We basically start with our width, or the top corner of the screen. The first pixel of the screen is 0, 0, and then the bottom corner here is the width and the height. So we're sort of like going downwards, counting the height. So if I can draw an arrow, it's something like, the height here is positive numbers basically. So that's sort of like, if I can draw an arrow there, that, so every time you increase height. And now normally when we talk about graphs, we usually are used to, if I do it in another color and I'll rub it out, oops, so if I go in, okay, let's select line again, and this time go orange. Normally we're used to kind of like starting from this bottom corner and going upwards like this. So that's what we're used to. But pygame, but actually not just pygame, all of these drawing modules, everything that has a screen in it, basically the screen always starts here, and it sort of like goes across width. So over at this point here, if I do put text in, this is width. I will change that to green again. There we go. Width. No, you didn't change it. Okay, hold on. Let's just get. This is the width, and the height here is 0. So that's this component, and over here, this would be, if I go to this corner, it'd be the height, and also, so the width is 0 because you haven't moved across at all, and the height is h, so it's 0, h over here. So that's basically the shape of the screen. But anyway, we're going to do something new, so let's just, I guess, delete everything here. Well, what I'll do is I'll cut that out. Cut it. I could put it into a drawing object. Okay, I'll just put it in a drawing object on the side, although it's probably not so useful there. Delete. In fact, I might use this drawing platform. This is LibreOffice Draw, so I've kind of like got my picture there. It's just that I can then keep the pictures, so I can sort of like move on and do the next one. So let's just create or view page pane, and to like create a new page there. And what we were talking about was this GMM over R squared, which is basically, so if I have like a particle here, and I will, let's just fill it. I wonder if I can do the fill from here. Area, none. There we go. So that's kind of like one particle. And then I will copy this and paste it. And here's another one. And here's another one. And then they are of different sizes as well. So let me make them. We'll make a smaller one here, like that. And I made it too small. Yep. So something like this, and then again, I will copy and paste. So you've got this whole bunch of particles. They don't have to be the same sizes as we sort of like see here now. And maybe you have a couple of big ones as well, like much bigger than these. So copy paste, so like move that here, and we'll make that a little bit bigger. If I scale it from the corner, I think the circle's bigger. Right. So how does this system actually move, or what we're doing? And basically what we're doing is, first of all, we look in the X and Y directions. So we feel like we've got our theoretical grid. Now, again, maybe I probably will. I'll use the pygame construct. and not the graph construct. So that's our width axis here. So we'll actually label it even. That's what width. We'll call this W. So instead of having X and Y, which is our standard Cartesian coordinates, we're going to have W and H, which is our pygame coordinate system. So we're operating in the correct coordinate system, and our height here, which is then going to be H. So that's kind of like our system, and the origin is 0, 0 is here, so we kind of like know that, but let's put it in anyway. 0, 0. I wonder if that drew on the next piece of. I know that's fine. That went there. And what I'll do is I will just make that font a bit smaller. There we go. So that's our origin at the top there. And the first thing that we want to do, so we draw our bunch of stars in on the. We draw our bunch of stars. I need to make sure actually that if I'm getting any comments at all. So what I'll do is I'll click on that. And I'll go to YouTube. I wonder if I see the comment up there. The first thing that we want to do, so we draw our bunch of stars in on the. I have to mute myself. I wonder if there's a way of switching on comments on this. There is. Just because I want to make sure that that I get any comments on here. Stop. Just going to go back. Viewing live control room. Let's have a look at that. There we go. I've got a live control room, and yeah, it's on mute. So test. So I've got that there. If anyone wants to comment, then you're welcome to comment. So yeah, we're back at this, and so what we want to do is we want to first of all know our center of mass of the whole system, and that's going to be contingent on all of the masses. So this has got a particle and it's bigger. Let's assume that it's larger in mass than the smaller particle, and we can sort of like do its mass times by its distance from the origin in the W direction, and its distance from the origin in the height direction. And this could actually be 3D. And so and our usual Cartesian coordinates are kind of like here. We got this one here, and paste that because then I can do another version over here, which is our Y, and then paste that again, and sort of like that. That's our usual coordinate system, which is an X, a Y over here, and finally over here is our Z coordinate. So that's actually what space looks like, at least three-dimensional space. But we're just basically, I'll move this a little bit further down. That's kind of like what space looks like. So I could actually make this, a tiny bit bigger on the screen. There, so we see both. Anyway, this is what space looks like, but we're working in this framework. We're not going to look at the Z components, although for the purpose of computation, we're going to have the Z components that are in there. And yeah, welcome to message, by the way, if you're in there. And we want to work out the center of gravity, and just sort of like eyeballing it. If I was going to do that, the center of gravity, if I was going to put, I'll put like, maybe I should put a cross or a star or something like that instead. if that exists. I don't know. There we go. I'll put a little shape in the middle, like a filled shape. Our center of gravity might be something like, you know, this purple cross over there. It'll be somewhere like that, which is the average weight times distance. It's the average weighting. I don't know where it lies. It might even lie on one of the objects, but it's our average weight times distance in the W axis and also in the H axis. So effectively, I guess I could draw some sort of dotted line there if I can. Just a regular line, which kind of like goes from here to here, and make that sort of like dotted line and area, and I guess it should have a color which will be like green. So it's sort of like that over there. That's its width. That's how far across it is on the that's where we measure it, and copy paste that, and sort of like there's its height if I can sort of do it right. So that's kind of like our center of gravity, and what we're looking at for each component now is this distance here, which is, so if I take like this particular star, I'm now looking at this distance over there, which I will make, we'll make that red. There we go. So we're looking at this distance, but that distance, and you know, we'll take another one as well, just to show like in a different way, but like this one here. We might look at this one here. So like these midpoints, okay? And again, make that red. But that's made up of two components. It's made up of a width component here and a, so let's do a dotted line for that. It's kind of like our width component, and it also a height component. So if I've drawn it roughly correct, I haven't, so I have to shift it across a bit. There's our, so that's our width and our height, and this is the this value here, this line here is our r squared. But what we can't look at it like, well, so we can look at it like this, but we're breaking it down into its x and y components on our Cartesian system, which is our width and height components here. So we're just looking at how far away it is, and we're looking at 1 over the reciprocal of how far away it is squared. So it's kind of like a measure. Well, it is a measure, because this hypotenuse is this squared plus that squared and the square root of that. But it's y distance, the force created from the y distance is from, this is the y component here, this vertical component, and it's that squared that we're looking at, 1 over that squared that we're looking at. And likewise for this particular one, and maybe I won't do this one, but I'll do, like, just because the lines look too similar there, let's click on that again. I don't know, if you took this one here, it's the same type of thing where we would have, I'll copy this one first, copy paste, and just pull a line down. It will be something like this, and again here, copy paste, it will look like this. And we're looking at these effectively these components. So that's what we're trying to do. And each one of these is, and we're calling this is our center of mass. So that's the important part. So that's the center of mass. Let's just make it all a bit smaller. So it kind of like fits in, and so like there. We'll make it purple actually, so that it matches. But that's basically our center of mass right there. We're looking at each star relative to the center of mass. Now we label each star, so this is index 1, index 2, index 3, like however we created them in some sort of order, they've got an index. And what we're doing in our code is a for loop, which is for particle in self.particle values, and we're going to compute this force. So that's the long-winded explanation of it all in terms of the physics of the system. But what we're trying to get to, or what we need to get to, I just put a test. I did put a little test there. Yeah, okay, fine. What we're trying to get to is over. It's over here. So this is the 1 over r squared component, but we're trying to work out our force. And one thing that I know that I've done that I'm going to have to correct in some way is, and again in the last video, like I set 100 particles, but each particle has a calculation in 3 directions, so that's already 300 calculations. And I go through and I do these for loops, a whole bunch of for loops, which I still need to think about. So this for loop here for changing velocities. But then there's another one here for calculating the center of mass. And again, we have to calculate the center of mass in the x direction, which is that one, then in the y direction, then in the z direction over here. So that's basically, so that's 300 calculations, this is 300, and we have to do this every frame. So it's not even every second necessarily unless we slow it down. And in our pygame module somewhere at the end, wherever it is, we set our frame rate, which is, we set it to 60 frames per second. Whereas if you down here somewhere, I think, clock.tick. And this represents, this is frames per second. Right. And you know, each one of these blocks is basically doing 300 or so calculations approximately. So there's 300 calculations for updating the velocities. I presume there's another 300 here because we're working on the masses of the particles. There's another 300 here because we're updating the velocities. So each one, so this is like 900. So 300, 600. This loop here is now 900 calculations that we're doing. They're not complex calculations, but nonetheless, it's 900 procedures that we're doing. When we move the particles, it's the same thing. We're looping through, and if we had 100, we're doing it times by 3 because we're working out an XYZ component. And likewise here for the center of mass, as we said before, if we did 100 particles, it's 300 calculations. So it's 300, 600. And then another, like, you know, couple, and then another, so like 1,000. We're doing 1,500 computations, and that's all being done in a frame rate of, I think this represents a maximum number of frames per second. So we've got to be careful with that. We'll read it in the documentation. And if that's the frames per second, basically we can pull out the old calculator. I don't have it up anymore, but 1 over 60 is the number of seconds that each frame lasts for, the speed that we need to do it in, which is 0.016 of a second. So it's pretty damn fast. Now we're doing a lot of calculations, and one thing that I realized on that is, or not realized, but you know, how can we speed this up? And something I mentioned in a previous video, well, if we're not using the Z component, maybe we could remove that. But for the purpose of actually having a proper system, that, by the way, is going to save us 30% of our computation straight off the bat. So we now have to. I've now got to decide, or we have to decide. Welcome to put comments in if you're watching, but you have to decide. You want to have that overhead of an extra 30% to have 3 dimensions. Although we're only going to do our modeling at least to start with in 2 dimensions. So we want to save that 30% or keep it in the calculator. But the other bit of it is that I do for loops all over the place, and in classical computing and in the statically typed languages, that's what you would do. You would do for loops, but loops in Python are less efficient because loops in Python use they use lists, and lists are not so efficient, basically, because they're not efficient in terms of memory and space. So they're much slower than if you're doing the same thing in C++ or C, which is the language where Python was born from. You would have to allocate a block of memory. So this is actually what we'd have to do. If I can pull this up again, if I find it. So we got a Python list here. Right, and it's mutable. It's mutable. So it lets us do certain things. So we can add elements where whenever, probably, and also and wherever we like. Right, we can do that, and also I better move this across a bit. We can, the elements can be of any type, and that's fantastic. We like that, huge flexibility. But that means that in terms of the memory space, we sort of like have this thing here. But like if it was an integer, but I wonder if I should actually do it with a text box here. If this was an integer, and I'll try and color the text box as well. Can I do a border around this text box? Some way I will be able to. Line, there we go, and style, so a line around it. Because this is actually a piece of memory space. So here's an integer. Oops. Copy and paste. Here's another integer. And here's another integer, and they're occupying their spaces in memory. Now this one here is a float, right, and it's floating point number, but it needs a little bit more memory, and we might have a string as well, and the Python list lets us do this. And that might even occupy a tiny bit more. I can't remember which one occupies more or less memory, but they occupy different amounts of memory. I'll actually make the integer ones a bit smaller, just for the sake of, like, visually, you can see that this is occupying less memory. In fact, I might even be able to stick in more integers now. Copy paste. There we go. It also lets us do things like stick memory in wherever we like. So, you know, if we wanted to create another integer, it might go at the end of the list, but we could shovel it somewhere into the middle. We could sort of like have an integer and go like, I want to put this integer along with the other integers, sort of like over here in the list. So if I can get a line, I want to stick it in there. Right there. And the Python list lets us do that, so it's really, really flexible, very, very useful. But now the list doesn't know how much memory it's going to consume, so this is sort of like this is kind of like the memory that it needs to allocate. I'll move this all to the back. Area or arrange, send to back. So it's kind of like that. So this is the, make it a very much lighter color as well. So this is the memory that has to be allocated to it, and it doesn't know what to allocate. So it's kind of like an inefficient process. It has to put in lots of redundancy and so forth. And the fact that you could stick something anywhere into the list means you can append the list. Whereas a C++ list, which and Python has access to this because it has NumPy. So, and really I'll actually refer to that, which is NumPy. A NumPy list is much more structured because you have to do this, which is you have to, over here, force the types. So you can only have, or only has one type. So it only has one type, right? So now you've lost your flexibility on types. You can't stick in a float and a string and an integer and a boolean, even whatever you wanted. You can't do that. It has to be all of one type, and cannot change has to be of a fixed size. Must be fixed size. So it's a big deal to allocate a new size in a NumPy array. Not a big deal. You'd have to find a new bit of memory, like remove your array and create this new array. So now this NumPy array kind of like might look the same in terms of space, like this, but actually now it's more like, oh sorry, I'll take that back. It would essentially, if I can do the highlighting on this, I wonder if I can get a select. There we go. Copy paste. Now it looks like this. Okay, and a whole bunch of integers. It's much more efficient, and you can operate it. So in the space in the memory, it's one contiguous, and these things, by the way, are now in different parts of the memory. They're not even necessarily contiguous. They're not next to each other. They're just scattered around the memory as part of the list. But this is one contiguous block of memory, so it has an advantage. The advantage is, if I can make it wider, of memory. Right. And this is what we need to achieve to get some speed. So this is what I've been using for the purpose of, and it's really, really convenient. It's not like, it's not, I should say bad practice. It's not bad practice. You know, Python was invented, or like one of the usefulnesses of Python is that you get this huge convenience, but for this convenience you're trading off speed, basically. So I'm over here casting everything. In fact, I've got a dictionary. Now, a dictionary works, should work faster than a list. But what I actually create, and this is all about data structures really, and not about the code. So I'm going to have to go back and fix this to optimize it. So it worked on the laptop. It doesn't work here for a different reason. I don't know what it is. It could be a graphical reason. But apart from that anyway, I need to think about a structure. And it'd be good for anyone viewing this now or later if you post comments. But think of a structure that operates a bit faster than this. And the reason why I say that is because, where is the number of particles here that I defined? So I sort of like call it somewhere. Here's this actual simulation. And in the simulation, you know, we set up our system here. So this is the actual piece of code, and I'll sort of zoom in on it there just so that we can see it. This is our actual piece of code here, where n, and if I sort of like hover over it, I think it should come. N is the number of particles, and I spelt the word default wrong, default. So go to definition and change that to default. I wonder if sometimes you can go back on this, go to definition, because it is the definition, finding references. Oh, it is, it's going to find references, hopefully. I find it quicker sometimes. I don't know why it's slow. Oh, there, it's found. Let's class system. There we go. Right, we go back. I don't know why that was so slow. It's happened a couple of times now, which is a little bit annoying because you still want to click on it and go there fast. But anyway, that's the number of particles that goes into the system. And I just set a default is 10, this if you leave no number in there. But like, here's 50. And even with the lines, if I do F5 to run it, right, it's okay. It's sort of like it's moving and it's working. Okay, ignore the lines, the annoying lines at the moment. And it'll get to like loop number 500 and close, but I could close it earlier. There's me. I don't know if I closed it earlier or not, but whatever. But I could do like 200, right, and hit F5 again. And it pops up, and you can already see that it's a bit bittier and slower. You can see the loops actually going slower as well. So it's all slowed, everything's slowed down. And I think that kind of tells us this is the max frames per second. I'm quite sure that it's the max frames per second. And what I'm going to do is I'm going to go into Bard if I've got it open, which I do. And I was looking at some type hinting and stuff, which is quite pertinent to this actually as well. But what does do in the pygame module? I shouldn't use Bard, I said that before. I should actually look up the documents, and I've got the documents, but let's just see. I'm hoping that it kind of like corroborates me. I'm hoping I haven't actually convinced it somewhere else above in the chats I've got. But here we go. Clock.tick function in pygame module returns a number of milliseconds that have passed in. Oh, okay, fine. If the argument is the default is 60 frames a second anyway, so I could have actually left it blank. I think generally, I don't know if this is completely correct, but I might. I've got it here somewhere, like pygame. I've got a whole bunch of different things that are available, or whatever, because I've been looking around. Real Python. Playing recording sound in Python. So I'll go back to pygame, and well, I could go to maybe the documentation. Instead switch to the tab, but I wonder if I got where is the clock thing there, because it just mentioned clock. I might even put it into the search bar here, because it's got a little search bar. Clock. Pygame.time.clock, right? This is probably a better way than Bard, but I wonder if actually Bard actually took the, because this is from the Pygame module, so it will tell you what it does. You can set your frame rate in milliseconds. Where's the actual description of it? Pygame.time. Create a clock object to help track the time. Okay. Okay, did I set the what am I talking? I mustn't confuse the ticks with the actual setting up of the clock, so let's just be careful about that. Clock.tick. Okay, so I need to look at clock.tick, which is this one here, and you put your frame rate in here. So this method should be called once per frame. It will compute how many milliseconds has passed since the previous call. So I wonder if that is actually 60 milliseconds since the previous call, because that's what it's saying. If you pass, the optional frame rate argument will delay to keep the game running slower than the given ticks per second. Calling clock.tick once per, by calling clock.tick 40 once per frame, the program will never run at more than, so it is a maximum here, will never run at more than 40 frames per second. So it is the maximum frame rates. That's what that is. Let me just do a shift and sort of move that there. So this represents our maximum frame rate per second. Now, when it was at 200, it was sort of like slowish, and if I sort of like go to 300, I'm going to hit save just in case I break it, and do F5 again. I'll increase it slowly until I crash it. But look, it's going really slow now. That's annoying, and presumably it's because it can't handle. We can see how slow the loops are going now. You can literally see them like one by one. And I reckon I've just closed it there with the cross. If I go to 350, I wonder at what point kind of like it sort of like freezes. It should still, you think like, I wonder if I actually pull in as well over here, but my processor's running high because I've got other things going. But I wonder if I can actually, on the processor itself, look at the processes and if there's a VS code. Because I'm going to look somewhere down here and see if there's a VS code and sort of like observe. I wonder if it will jump to the top when I run it, and then I'll be able to identify it. I have to put it onto the side for now. But anyway, this 350, if I hit F5, yeah, I've identified it now. But we can see it's basically getting really. So these lines are really annoying, by the way. Like you couldn't have a, you know, the simulation doesn't look nice on this screen like this. And anyway, that's what we're going to address. But yeah, you can see like I'm grinding it to a halt there, and that's just with 350 particles. Now a galaxy and a galaxy simulation might be. You know, it will be thousands and thousands of these things, and we should be able to compute it a bit better, and we have to do some tricks now. It will never handle this bigger stuff, even with like way faster processors. And I did something like this like 20 years ago, back at Imperial, if not more, 25 years ago at Imperial College. So our processing power was way less, and yet we could still do, in a way, better graphics than this. But this is one thing, because I was looking at this entire pygame module, and I saw like I even had a video of it going on. Although, yeah, I mean, and what I've realised is pygame is great for games, but it's less good for simulations. And the reason why is when you do a game, you tend to have in a game. I'll draw it here maybe because I don't need this one, so let's get rid of all of this. In fact, hit delete. There, it's all gone. In a game you might have kind of like one character, so you've got your background, so let's just do a background fill. So that you've got your background there, and you know, here's some ground or whatever. Let's just do some ground. I'm going to draw some really cheap, nasty background. It's like, here's your ground. I should have filled that. There we go. Oops. Right. I don't know how to get a solid object here. There we go. Shape outline, shape fill, solid fill. There we go. So. Okay, that was terrible because I want to fill it brown and brown. There we go. So like that. There we go. So that's our, and that's our ground. And then kind of like you'll have this like a character. So, you know, something like, I don't know, like a ball or something here. We'll do like, I don't know, a square that moves across, right? And basically all you're doing is this. You're like moving the square across the ground or something. You're driving your car. So in terms of the simulation and a number of computations, it's actually not that much because you've got this object. You still like define what this object is, and then you just say move the position from here to here. That's one step, and another one, another one, another one, another one, and so forth. So you're just doing these little incremental steps, and that's it. So the number of calculations is far less. Whereas when you do a simulation, you all of a sudden, like in the simulation that I had, which was over here, you've got this many objects, but like I've just set this to like 100. Now I've got to do 100 calculations in 2 different dimensions for each of those things. So now I have, or 3 different dimensions. I have to do 300. But and that's just for the positions alone, for like getting the center of mass. And by the way, the center of mass needs to be calculated every time because the center of mass might be moving if the average velocity of all of the particles, so sort of like a wind or a drift. If we had a drift, let's just color that in a different color as well. Might leave it in, there we go, a lighter color. If we had a drift in this direction, then all of these particles here, so everything here, I'll move this down a little bit because I might be able to do this, everything here would move across. So all of that over there, and this whole system would move. So we need to keep recomputing the center of mass, because now everything's drifting across. And likewise, if it was drifting downwards or even across and down, we need to do the recomputation for the center of mass, because we're concerned about, like, the distance between this particle and the center of mass. So we need to know where the center of mass of our system is at all points in time. Now, I think, having said that, there's probably a trick, because everything is probably always relative to the center of mass. And that might save a lot of calculations, because that will save an entire loop's worth of calculations, because we could say that the center of mass is stationary, and we just want to look at everything relative to that. And then we could just say, well, if it's stationary, that we could plot it at a fixed point all the time and just look at all of the relative motion. So I have to think about that, because that could save a whole bunch of calculations as well. But nevertheless, we need to look at these respective positions. Actually, I think we're still going to have to compute it, because everything's always going to be moving. That would save us one bunch of calculations. It wouldn't be too ground saving compared to other things. But then again, all of these efficiencies add up. So it's just something to think about. Do we want to compute the center of mass once and kind of like fix it at a point, and then not have to ever recompute it, saving n calculations? However many particles are in our system, we just save that many calculations straight off the bat. So that's something else to think about for the purpose of not just physics, the computational physics, because that's our cost in implementing this. And I did find my VS Code on the side. It's kind of like over here. I wonder if, can I double click on it? No. So like expand resource values, memory. No, because that's just for that. Expand a whole bunch of things. I wanted to sort of like see how much it was costing in terms of memory just for one application, which I don't see there straight off the bat. So anyway, there will be a way of doing it, but I know I've got to get these efficiencies into this system. So we're going to go back now to back to the code, or back to where we were. So over here, we're back where we are, and we know that our system gets very slow. Now, we're still focusing on getting rid of the lines, and I went to the original documentation again, and like in the previous video, I've done this, so you can go and look it up. I sort of like copied this bit here, which is our quick start guide, and that kind of like worked. That was good. Then I did this, which was something where you could sort of like move a circle, and inside of that I added some random dots just to simulate like some dots on the screen to see if I'd get the horizontal lines, and that's kind of like where I got to on that. So that was all of this piece of code here. So I'm now doing a test because it didn't work the first time. So and I implemented something else. Actually, something came to my mind, for the purpose of tests and so forth, which is, again, the tutorials that you look at, and especially for tutorials on things like pygame. And I'm not watching like a 3-hour tutorial, which I'm like, great tutorial by the way, which I'm like an hour through or something, like, or two hours through. But the guy's written everything in one script, and he's barely written any functions. So everything goes into this long, like game module. And it might be considered to be poor practice to have really, really long functions. What you should be doing is breaking down your code. So, but the reason it's done like this in a reason, again, Python has a level of convenience, so we like the scripting. We don't want to put things in functions, we just want to like write them as scripts. And even in the example actually over here, it just puts it as a script. Here's a little script, and this little script will there's no functions in here at all. This little script runs as is, and you can sort of like copy and paste it straight into your Python code and hit F5 and run it, and it will run and it will work. But the minute you want to start doing other things, or if your game became a bit bigger and you wanted to like do other implementations and other stuff and replicate code, if you haven't used functions, then well, you lose the ability to have functions and classes. Right? You just lose that ability. Now, everything's here is at what's called the global scope, basically. Um, and with, nothing wrong with that. It's all at the global scope. But when you create functions, they're at the local scope. But then you have an issue. So, and this is like, and it doesn't cater for these in a lot of these basic examples. How do I, like, for example, if I've got this, and I want to sort of like export this little piece of code that deals with, you know, and here, this piece of code, I'm going to say should be a bespoke piece of code, right? It should have a little comment on it in some way. But what this actual piece of code does here, some people say, well, you don't need a comment, you don't need anything, it's really obvious and intuitive. But what this piece of code here deals with is moving, like, so this thing here, here's a slightly more fleshed out example which shows you how to move something, a circle. So it's going to move a circle around the screen, and we'll see this working. But this piece of code, you might say, belongs in a function because maybe I want to do other things. Maybe I want to have like an extra item here, like Z, where if I press the key Z, the circle gets bigger in size. So say its diameter increases, and instead of moving, it gets bigger. And if I press, I don't know, Y, then it gets smaller. So something like that, or it changes color. You know, if I press C or something, it rotates colors and things. So all of a sudden, this thing here, which is okay, it's compressed and it's small and it's great for the scripting example in a script. I don't want to take that out and put it into a function. So I was kind of like, I'll play around with that as well because that's an extra thing. If our module is going to get big, it might get big. We don't know. If you want to do any extra bits, bells and whistles, you need to have a way of getting this out of the script and into functions. So I kind of like also have made an attempt, at least a beginning attempt to do that. So you see nothing here now. There's nothing in the global scope apart from import and import the two imports, pygame and random, because I use them both. So what I'm going to do is I'm going to just do a quick retweet on Twitter if I can, just to make sure that not there. How do I get the link to this chat? I'll just do a retweet, I guess. Right, there we go. I found my thing, and I'm just going to hit retweet. Ah, hold on, but it's a live coding session, right? Retweet. Retweet, there we go. Right, so it's back out again. Which is, I wonder if I can copy link address. And I'm just going to do a Twitter post. Create post. Here is the link to the here is a link to the live session. Right, I think that should work. I actually wonder if I'm just going to attempt to click on my link, my own link, just to make sure that that link works. Yes, it does. Okay, good. And I think people can post in it as well. I wonder, have I made the chat visible for everyone on here? So can everyone see the chat? Back, okay, possibly, maybe not. Hello. There we go. So I'm wondering if that goes into the chat or not. I'm just going to go on to the Twitter session and click on that one more time. Just verify if it goes in or not. Oh yeah, it does do. Okay, fine, it's all there. So we get back to it, but basically, like, so this is the module, and I've got this the game version 1. So that was the original version, which was basically, if I go here, that was this top one, and so that was version 1, and that worked. That was all fine, and this is version 2. And that worked as well, and it's all fine because I can show that it works. So this is the actual game here, and again I've put it into these. Now there's just 2 functions. So if I go here and in particular over here go to here, we can see in the outline we've now got a main module, which is this module here, and all the main module does is call a game. And then we've got the game version 1. Well, we're not using that anymore, but it's there. It's available if we want to use it. So if there was something that we wanted to have. And then this is the game over here. What have I got? And then I created this extra module because I thought, like, well, maybe I want to write to the screen more times or something. Anyway, just testing. Can I stick a module in and kind of like call that module? So instead of having all of this code, which is write to screen, maybe I want to export that because I want to write to screen in different types of ways, and I want to do it several times, and I don't want to have this piece of code getting really, really big. I want to export all of that out, and I think I can get rid of that, in fact, because I've got this write to screen here, and it passes in this variable counter over here, and it does all of that code over there. So I could comment this all of this out, and now this code, in fact I could cut it, and just remove it altogether. Now my code is a bit shorter because here I can go right to screen. I've documented it properly. I've even type hinted it, so his screen takes the surface. It's the pygame screen, and the message is the message that you want to write. And okay, this little bit's gone. Let's have a look there. This always happens, actually. I've got to be careful. But this bit here, and I paste it at the back. I just want to make sure that when you put something in brackets here, I think if it was before the colon, it would be fine. But this is an optional argument, basically. So over here now we can see that, because I want it to look nice as well, screen, the pygame screen, message, the text to write, and font, which is a pygame font to use. But it's optional, so if we set none, we get the default one. So like everything's now exported out into this function, and I've got this kind of like nice thing. So all I have to do really is pass a screen and the counter item into it. But that was just sort of like an example of that. But now I can I'll run this anyway. But what we're looking for is to not get lines in the code. And then I'm going to have to now start putting things in. So if I hit F5, it does a bit more than the circle on the screen. It does these little yellow dots as well. And I can, it's not with the arrow keys, it's, oops, where did I click on that? Did I just, I switched it off. Because of that here. I might just, I'll make it 1,000. So you've got 1,000 things, just so I've got a little bit of time. It will stop itself. Again, that might be an argument that you want to put in here, sort of like, how the game, run it for 1,000 loop, how long you want to run it for. In fact, I might put it in here. Loops. I call it loops end, and it's an integer. I'll type into an integer, and basically like here. I'm not going to call it a game. Loops until the simulation. You wouldn't do this in a game. because you don't want your game just to end, right? So now I need to take loops end is an integer, and I'm just going to set it to 1000 if it hasn't been defined, right? Because it's an easier way of doing it. Because then where I call the game, which is in the main module up here, where I call the game, it's already got, so if I didn't put in a number, so I could put in 250 and overwrite it, but if I didn't put a number in, it already populates it with 1000. So I just go back to the game itself, and I'll probably rename that as well, but yeah, let's go back to it. It's down here anyway. We see that this is grayed out at the moment, but that's because we now want it to, if count as greater than loop said, so now we don't have this thing here. And also this 1000, like it got highlighted when I clicked on that, it's got nothing to do with it. This was the for the purpose of the physics, number of frames per second, which I need to get my head around to make sure that that's working. So this will now run for a bit longer, so I can talk about it for like a bit longer. I've got until this number here gets up to 1000. But we don't see any lines here. These are just random dots that are appearing, and if I do W, the circle goes up, and if I do S and D, so you can sort of like play around with it. I can even go in a diagonal actually, although it's not actually, remember, it's not going in a diagonal. And there we go. And I hit a few times because I was still doing it while it was running. But that's kind of like, so yeah, you wouldn't do this in a game. But you might do this in a simulation, or you're to like have it sort of like exit the simulation in a graceful way or something like that. But that's kind of like what this is. It's sort of like my graceful way of exiting. All it does here is it basically sets the running, which is this while loop. It was true. It's because running equals true. It sets it to be false basically. I should really actually move this running equals true, because it's usually, I don't know if it's good practice, but before you enter the loop, the things that are like sort of like pertinent in the loop kind of like go there. Where's player pause in this thing? Oh yeah, player pause. It's something about it's a screen width and height. Okay, so okay, these are all things that need to be entered before you go into the loop. Anyway, so it's just a bit more obvious. But basically, running equals true, and then at some point, running equals false, so it doesn't continue the loop anymore. So the while loop ends, and then it goes to pygame.quit, and that's kind of like the end of the game. And we could even like log or write a message or something at that point in time. So that's it, and we have something that's working, and we didn't get the lines going across the screen. So now really is the point of implementation after a whole bunch of reviewing as to what do we do from here. And in fact, I might even remove this. Right, there we go. I've now exported that out, so my module's a bit smaller. I don't need this. I'm not going to do flip. I'm going to do update. Again, I explained it in the other module. Update certain areas. Flips the whole, updates the whole screen. The reality is if you just do update and you leave it blank, it does flip anyway. So I'm just going to put update the display, right? And that redraws the screen. That's the screen redrawing process. And yeah, that's it. So now we have to start putting in our code in somewhere. So here it says in our example above, it needs to go into the into this while running loop, which is here. And this is the point about having it being functional, as in functional as in having functions, is that imagine that I try to put all of this effectively, or large parts of this, into the loop. The loop would get very big very quickly. And I wonder what I did. I've got to remind myself, yeah, I've exported that out to different, like, I've made a class basically here. and the class was for our for the system, which is all of this, and then it could sort of like do where is it? The class is right up here, and then it can do a whole bunch of stuff. So we can run our function. So I could kind of like call it in, and that meant that all of this, like all of this code, which is absolutely necessary for all of the physics of it, could remain outside of the actual simulation game loop and like our computations. But heavy crunching is done here, right? This here is heavy crunching, right? Because basically what's happening is we need to draw our particles. So we draw our particles when they first start. Then we do a whole bunch of procedures on it, which is we move the particles because we're given their initial velocities and we need to move them all. Then we need to work out the forces on all of them. And from the force equals minus gmm over r squared. So we need to do that. We need to compute the r squared, so all of that. We need to work out the forces. Then we need to apply those forces to create an acceleration, which changes the velocities. And then those velocities will be used again at some point when we go through the next loop. So we have our next loop. In the move particles, we have updated velocities for them, and that will cause what looks like an acceleration in the system, which is exactly what we want. We want things to move in curves or whatever, like rotate in some way around our gravitational field. But this is heavy crunching here, and it's a lot of lines of code. When I say lots, okay, it's not a huge amount, but it's enough that, you know, this module, this piece of code here, if I can, let's make this, get rid of this on the side here. You know, our simulation is from 230, it's like 30 lines of code. And now this is the bulk of the code. So this goes from, I don't know what it goes from. This class is actually quite big. It goes from line, I mean, it's not huge, but it's 100 lines of code that you've kind of like exported out of the simulation. So I'm going to try to do the same thing. But again, I don't know if that's what broke it. But at the same point in time of doing that, I actually need to start thinking about doing, I actually need to start thinking about the physics of it as well, or the computational part of it. So one, have I got the physics right? I think the physics is correct. And number two is, have I got the computation right? Because somewhere in here, in our test pygame, I'm going to try and do something like, so we just got some random variable, and this is quite inexpensive coding wise to do. I'm going to interact the particles in some, or these like random yellow dots. That's what I'm going to attempt to do. So if I F5 it again, run for 1,000 bits or whatever. But instead of just having these like randomly pop up, which is very computationally easy because you can like make a 1,000 random dots quite easily, I'm going to sort of like make them interact with each other. So let's close it early. There we go, just to show that I can close it early as well. And over here, I might need to start putting things in. So we're not going to have these random variables again. And again, I might make a, we'll call a function. We're going to make a function here. So we'll do something like, because we want to do our heavy crunching. Tab, some computational complexity. Right, this is going to be heavier. There's no spell check on it, so computational complexity, yeah, typos everywhere. Got in comments you can get typos because there's no spell checker. It'd be nice if actually a spell checker came on, like if there was so that I don't know if there's a spell checker in VS Code actually. Be a useful feature because I'm forever doing typos. Although it might annoy you as well because certain words kind of like they're not English dictionary words, so you'd start getting red squiggly underscores everywhere for your spell checking thing. And some people would argue that that's not part of what coding is anyway. But we want to put in some computational complexity. This one was very light, but let's just put in define a function, and I'll call it something like connected particles. Right, so something like that, connected particles, and let's have a look at that. Right, for the connected particles, function which operates all the particles in the system. Okay. And one thing that we wanted to do, so we're going to like export this out now, wherever it was up here. First of all, we might set number of particles as a variable, right? So we now want this to be a variable that comes into our thing, and so num particles 10. So something like that. So this anyway was num particles, right? This I thing here is a placeholder. Nothing really happens, but maybe we can do something with it. Well, they're sort of like the labels in the particles. So like particle 1 is, well, it starts at 0, so the first particle is index 0, the second particle is index 1, and so forth. But again, we're going to be exporting this to a NumPy array, but we can practice with that in our computational complexity. So I'm going to just try for the moment just to, so one of the things that we want to have is num particles. Okay, there we go, which is an integer. Okay, and here we got num, it's actually the args first, which is num particles, which is an integer. I don't need to say it because it's already type hinted here to being an integer. I prefer type hinting than to put it into the docstring now, I think. Someone said, like, DRY, do not repeat yourself. You know, I'd say, like, because I asked a question about type here, like, you know, how should you comment? Should you put the type in the comments, or should you put a type as a type hint? And somebody said, well, whichever you do, don't do both, because you're kind of like repeating yourself. I like it in the docstring, and there's a reason that you might want to put it in the docstring, which is that if you had an auto documenting thing afterwards, it might not catch everything that was here in the arguments, but it'd catch it all in the docstring, and then it would label it nicely for people. But anyway, I'm not going to label it here. I'm not going to call it an integer, but it's the number, basically the number of particles. Right. Now, again, this is for the purpose of taking everything out of here. I wonder if I can just do this. Well, first of all, we're going to, what was that module called? Connected particles, right? So we will do connected particles. And also, actually, in our connected particles, over here, just in case we do forget to put anything in, we might just say that there'll be 100, right? There we go. So the default. Right. Again, I'm probably repeating it. Like, do we need to actually even say that now? Because when you sort of hover over it with your type hinting, it already says default is 100. It tells you here it's an integer and it's got a value assigned of 100. So yes or no, do you need it? So, you know, I could have had this int that's kind of like the full doc string. So now you see number of particles int number of particles, which is the number of particles, and default equals 100. But the reality is if you're reading the code and it's already sort of like telling you what a lot of it is. You could have both. I don't know. I'll leave it as it is for now. I wasn't putting. You know what? I'll leave it as it is. So the next part is let's go and take this piece of code from here. And this is the thing, because I put it into a function, I've got one level of indentation. And now we've got this while running loop. So we've got another level of indentation. And then we've got a for loop, and so another level of indentation. Then we've got an if statement, another level of indentation. So we've got 4, 8, 12, 16, because Python works on white spaces, and the standard indentation for Python is 4 white spaces. I believe Google uses 2, so it would be half, but you've just used up 16 characters from your line for the purpose of indentation. Whereas if you export to a function, it's not so deep here, but it can get deeper and deeper. If we export this to a function, so I can take that and put it into the function, it reduces it back down, which is paste it there. Now we don't need all of that level of indentation. And one thing that we need to pass in here is the screen, and because it doesn't know what screen is, and we might be passing this around left, right, and center, but basically, if any of our stuff that we're passing through, I pass it into the thing that controls Z. I meant to pass it into here, into the argument over there. So something like this, where screen, okay, and if we go to our pygame documentation there, but where is it? Unlike some library, I give you that. I just wanted to say what screen means. But it's a pygame display. It's kind of like the main screen that everything is written to. I might do because they're different screens basically. You can write screens on smaller screens, so it kind of looks like this. I can't remember what the actual wording was for it, but the pygame module itself has a screen. That's not text, so let's just right. This is our pygame screen, right? It looks like this. Let's make it a lighter color though, so something like that. And this is actually the screen here. Okay, so that's kind of like our main screen. Main screen of pygame. But then when we want to put objects onto the screen themselves, so we need to put them on as like rectangles, so like this, and maybe another one as well. So I just do another one, so like over here, and it's different shape and size. But these are also screens, so these are like object screens, or so the screen goes onto a screen. So we need to avoid confusion of screens. So this is like an object screen, and what I will do is shrink the code, shrink the thing. There we go. It's like size 10 there. Get it small. So this will be object screen 1 over here, and this one might be object screen 2. So we're putting screens onto screens. Object screen 2. So it kind of looks like that, and the reason that happens is because you might want to at some point like move your screen around, so it's like move it and place it. And that's the animation. Is the object screen 2 might be have a character in it and it might be moving. So it might have a picture of a cat or something like that. You know, there we go, a little smiley face in it. So it might be something like that. And our object screen, we want it to kind of like move now. So like our object is a smiley face on the screen, and we select want it to move. So we've got screens that go on top of screens. I've just called it the main screen, and these ones like the various object screens. I think that they're actually called rectangles here. Because they are actually rectangles, you place them and you place things into the rectangle. That's kind of like how sprites and things are done for the purpose of gaming. We're not doing gaming, but that's kind of like how it works in the pygame module. So anyway, in our code, we need to make sure that if we are going to have these functions, and I sort of like had it on the test one over there, I wanted to write something to the screen. Our original screen, or I'll call it here the main pygame screen, is what we need, because that's the thing that everything gets written to. Like all of our objects go onto this screen ultimately. So we need to pass that in, and that's not optional. So we need to pass screen in here. So go to definition. Oh no, not go to definition. I want to actually go to references there. But let's just scroll up anyway because it'll be there. I now need to pass in here screen. And in our case, screen equals screen. Right. There we go. Screen equals screen, but we can pass it in. So, and our screen here is right at the beginning, our display, our original display. And I'm going to start amending this in some way. I call it, I guess, bastardizing it. I'm going to start amending it because it's quite nice. It's quite a cute thing that this code has actually done, because it actually gets the width, but that's going to be a bit annoying left, right, and center everywhere. And what's typically done is you have a height and a width. I'll call it height and width just for not ambiguous. And it's equal to this value here. We'll just set it equal to that so it hasn't changed really. And 720 over there, because then we can use the I've got to be careful about which way around this set mode goes. Actually, set mode make sure that size coordinate it is width and height, so and be careful, width and height. There we go. Nearly got that one wrong straight off the bat, and then everything would have been the wrong way around. So here now we can do width, because we want to take out all numbers. We want to be this to be as arbitrary as possible. So, and height. Right, now we could get the screen width and divide it by 2, but now we sort of like know what that is. And if we wanted to do something like that now, well, it's kind of like we don't need this get width anymore. So we could do W, H. I'll do that as well, just so that these are available to us, right? Is it just that we've got this, but all that this is get width. Because I like that. I might put the center, like the W center, which is like the middle of the screen, basically. W center and H center. Okay, equals get screen width over 2. I'll probably put it onto 2 lines actually, just because. X that out. I'm moving it onto 2 lines just because just a little bit clearer, it will overrun. Like, so it's nice to put it on 1 line and use this tuple unpacking. But now we've got like this, so we don't have to have this everywhere now, which is bang, go away, and right. Now, I don't know, just in case I broke everything, so like hit F5 and run it, it should all still keep running, I hope. It's all running. There's more particles in here, but that's just because I set the default value to 100. But we could overwrite it if we wanted to, wherever we called our function. I don't think the number of particles is 10. Hold on, connected particles screen. Okay, yeah. Here, basically, we've got 100 particles by default, but we could have num particles is 10 again, for example. But funnily enough, we'll get these extra 10 because I didn't remove them. So let's just comment this out now, because I don't think any of that's needed, because that was all now exported into this function here. Right, and I'll now hit F5. It should still run. Yeah, there we go. We've got 10 particles again. I think if I phrase it like that, you can see, you can count them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You can see the 10 particles. I'm going to break the loop early. So, yeah, so there we go. We've now successfully managed to, we haven't done anything complicated yet. We still haven't got the green lines, but what we have done is managed to export our function that does some sort of calculation outside of the while loop, so that it can run inside of the while loop. So if we were going to do computations on these things now, like we could change them all to orange, for example, or change them all to random colors. We can make this function quite long now, which is what we're going to do basically. Because I still wonder why. Like I can't figure out why this one has the horizontal lines rendered. Like, I just don't get it. Like, why am I getting these horizontal lines on this particular one? Like, I literally have to replicate the code in order to do it, or rewrite the code so that it doesn't happen. So, saying that, maybe I should just create the class. I could even potentially export the entire class, but that might not be the best thing to do. And pass it straight back in to this bit here. That'd be a miracle, but it might work actually. So wherever the computational complexity was, I'd have a big fat dot here that was movable. I could remove them as well. The movable dot. Maybe I will export that as well. I wonder what I need to export that. The thing about moving pygame stuff in is, like, and this is the thing about computing, by the way. I really want to type in this to any, but like, you can't put any but message. I'll put it as it could be a string, and it could be an int, and it could be a float. It could be anything basically. That's my version of any. You could go to import. I could import typing. I could do import typing. I think, there we go. Or from typing, I should do really. From typing, import any. Right. And that would let me. Maybe I will. I don't know. I've been against it because I tried to use as few modules as possible. But basically that lets you do some additional type hinting. and then basically here now. The fact is that if I didn't put anything in there, it would go to any anyway. But I could sort of like any. There we go. Right, so it could be anything, which is the text. And the reason it could be anything actually is because in our particular version, it's just doing the loop message. That's all it was doing there. I might move it back actually, just right to screen. I'll put an int, right, because in our case it's actually an integer, and it won't harm it. But really, I could take this whole function and write more messages anywhere onto the screen with this function. That's the nice thing about it. But my string basically wouldn't be. My string would be more of this, which is, and then I want to pass a string in, and that's probably a better way of doing it. I wonder if I do that because I've got here it's write to screen, and wherever I export that write to screen here, I pass in counter. I could pass in message and sort of like create the message. Maybe I will do that because it's not really counter that I want to pass in. It is a message. So I'm going to say actually message string. There we go. It's going to be a string. And the message is some sort of string there. Well, it's going to be this basically. Well, I could even pass the whole thing in it like that. There we go. That is the whole message to pass through. And now that's kind of like type hinted correctly. And okay, I'm trying to why is my webcam output small? Hold on. You mean are the fonts too small? As in I can do this Control Plus. Is that better? I don't know if that's better or not. So I just spotted a little comment there saying, why is my webcam output small? I'm presuming, I don't know if that's referring to the font or not, or the size of the webcam used, but I'm using like a specific area, is what I'm using. I'm using kind of like this width, and I've kind of like fixed the screen to this width. So I can increase the font size basically, if that helps. I try to not increase it too much because then you can not see that much on the screen. But I can zoom in at every point in time. And the feedback's useful, by the way, because if you can't read it, then I'm kind of like nearly talking to myself on a lot of stuff. So thanks for that comment. I'm hoping now if you can leave a message and tell me if it's readable or not, then that'll be better. But where were we at? Oh yeah. I'm trying to, and actually this is a case in point. Why is your webcam so small? Because sometimes I overrun on this line here. I have got over there, I can actually draw on this on my screen. This red line here, right? That represents over here a certain number of characters, right? And the Zen of Python tells you that it should be, I think it's 80 characters. That's the world's worst piece of text, but I can't write text here, but it's 80 characters wide. And you really kind of like the Zen of Python, you shouldn't go over that. And actually, like a lot of people say, oh, you shouldn't, so forth. We've got wide screens, and normally I operate in this tiny little font, and I can go really, really wide. And it actually gets annoying sometimes writing onto multiple lines. So if you go over a little bit, it's fine. But if you like, because some people go through and they think that they're fixing code by doing this, and you should really be focusing on the code and not on going over the lines. But sometimes it's really useful because in a case like this where the screen size, we want the screen size to be bigger because your fonts are bigger. And actually when I was writing the book, the book has a certain width on it because you can fit a certain number of characters in, and really it should kind of like start looking like this when you are like leaking over the screen edges. So I should never, this boundary, I should never really exceed the boundary if I'm a good coder. And some people say, and that's another reason, by the way, for not having so many levels of indentation, because you would just have no space to write your code. And some people say, well, then you're writing bad code because you just got so many levels of indentation. Now here, we see something like, look at this variable with a type hint. This is my variable screen, colon, and then the type hint. It's all of this, and all of this, right? I don't know, it's a good 30 character, I don't know, 10, 20 characters long. So I've only been able to put 2 variables in here. But then somebody might say, well, if your line's that wide in the first place, it's going to be visually unclear. So do this, right? Split it up into the lines that it should be. That's kind of like how it should be anyway. I wonder if on the type hint, actually, yeah, it does. It sort of like type hints it down below anyway. So kind of like, or not type hints, when you hover over it, I wonder if it's called type hinting, the IntelliSense, whatever it is, it gives it to you like this. So it breaks it down in a readable format. And if it put it all across ways, you just won't be able, like, it'd just be ugly to read. So I guess this is the right thing to do. So I can zoom in. So thanks for the comment anyway. And let's get back to it. So where were we on this? Let's see. We were at, okay, I just did the screen width bits. Oh yeah, I was potentially going to move this across now. This is the next bit. And we've got to deal with this computational complexity too. So there's a couple of pieces to this. But this has nothing to do. Oh, we just did this as well, this loop counter. So that's where we were, right to screen. But I think that's all fine. So if I hit F5 to run it, it's all fine. Everything's running. That works perfectly well. And the loop counter's at the top. And it would stop at 1,000. I can still move my thing all around. So it's all working perfectly fine. It says loop.loop. Right, got to fix that. Why does it say loop.loop? Because no doubt. Right to screen, and then inside the screen, I don't need this anymore. Now I just need, in the right to screen method, I've taken in this message, and the message is a string. So over here, it's just, well, in fact, it's just message. There we go. So now when it's run, we just get the normal message back. There we go. So that's probably a better way of passing like the message in, and I can now use this. I can now use this anywhere. What I couldn't pass in, actually, funnily enough, because I tried to do this, was where you kind of like do this. The keyword arguments where you assign them values. So I wanted to assign this the value of something that was defined in the code right at the top, because where is it? Over here. I want to pass in the font from here. And in fact, the font actually isn't being used anymore. So I sort of like wanted to pass that in as the default value for the font. But yeah, well, actually, I can't. Well, I put, so if it's none. But what I could do now is write to screen. Where I do write to screen, I could pass in the font. There we go. Right. And the reason why I did that is, let's say I just wanted to be consistent with fonts all over. And this is very forward-looking. It's like too forward-looking. I don't need it. But let's say I wanted to be consistent with fonts. I can now set the font like globally, or not globally, like in this function, in our game loop function, effectively. I shouldn't even call it the game loop. I should call it the simulation. So I might actually change that, because although we're using pygame, it's not a game. For the purpose of what we're doing for the simulation, it's a simulation. A game's slightly different. A game you interact with, so like you play it and it does things. Here we're sort of like trying to model a real world physics system. So what I would need to do there, or what I've done it, well, I've used the font now and I've called in the system font and would use this font. But if I didn't call in this system font, what it would have done was it would have taken it as a none. But what I couldn't do is I couldn't automatically pass in that whole thing. So I had to do it like this because it threw me an error message saying that the font wasn't recognized or something like that, or it wasn't initialized. So if font is none, so if I did put nothing in there, um, and it kind of like defaults to none, otherwise it will use it. But now it's just going to overwrite this anyway. But F5 there to run it, and it will still run, and we still got the same font and so forth. Now let's say I did omit the fonts. Well, I didn't need to close it. I could, for example, have this at size 10. So if I omitted the font at the top, then it would at least give me a default version of a font. So if I left this one out, because it's not a not required argument, because we see here that fonts is defaulting to none, and actually maybe you should even write that. I wonder if I did. Yeah, well, let's say I put it's optional anyway, but it defaults to none. If I do that now, what we'll notice, hopefully, is that the font should be smaller. There we go. So I've kind of like got this tiny little thing there. It's actually quite cute. I might keep it that way. Um, yeah. So that's quite nice. So anyway, we're exporting bits out. Now, can I export? So this is real time. I literally don't know if I can or can't do this. Can I export this out in one go? So I can make another function. You could argue that this all goes into a class, really, because they're all related functions. And if it did go into a class, it'd have the advantage that I wouldn't always have to pass through this screen message, because you're always writing to the screen at any point in time. But I might make, let's have a look, because we could have just something here just to remove some of the stuff, but it's called player position, right? So def, we'll define a function, def and player position. Okay, and in the player position, so I'll just call it, yeah, we could keep it like user position. There we go. We're not a player anymore. In here, the position of the user. I could call it a spacecraft, like spacecraft position. It could be anything. At the moment, it's a white dot. But basically, in here, I need to take in. So I'm going to copy it all so that it doesn't break. In the user position, this. Okay, and the first thing is, I'm just hoping that this is indentation, nothing else, but I don't think that's the case. Something like this, but it's taking player.pos. It needs that because it's squiggled, right? So keys player.game.key pressed, that's fine. Pygame.key.key pressed, but player pos was defined somewhere. And I can actually go to the definition here, go to definition, because I'm going to need to pass it in. I need to pass in player pos, which is of a certain type. And this is a bit that might throw me or not throw me. But I need to get player pos in here as one of the arguments. I wonder here. It's just like a vector actually, with x and y, but it's a pygame vector. I should probably stick with the pygame vectors. And actually, one of the things that I did in this n-body simulation is, because I'm new to pygame or I haven't touched it for years, is I made my own vectors, and funnily enough, they look very similar to this pygame vector over here, which is a vector 2, and there's probably a vector 3. I imagine this is vector 2 for the screen, the x and y components, whereas I had vector 3 for x, y, and z components because I wanted to do, in theory, a full simulation. But this is more visually for getting it onto the screen. So I presume there's actually a pygame dot vector 3. There we go. And I presume that the pygame vector 3, well, it's a sequence there. If I hover over it, I presume I would have thought it was just an x, y, and a z, because vector 2 here is a class there. I just wonder if I copy all of that. Can't like put it here. X float sequence float vector 3 equals 0. X, I'll put 10 comma 20 comma, I don't know if this works or not. Oh yeah, here you go, x, y, and z. Now it's doing it. Right, there we go. I wonder if I put in another one, 40, what happens? No, okay, fine. Then it breaks it. So at least from the type hinting point, it's an x, y, z, and it's a vector basically. So it's something that's given to you by pygame, so that's quite useful to sort of like have and know that's available, because actually what we're computing is in 3 space. But I need to pass in this player pos over here. I need to have it, and it's going to be a pygame. I need to know what sort of class it is. I think it's a vector 2, just a vector 2 class. So this is of type pygame dot, oh look, there we go. There we go, and that looks like it's just type hinting it, so it kind of like works now. So this user position here now is going to pass it, and it also needs dt, and dt was that variable used for the purpose of physics somewhere here, which is it's set right at the top, I believe. dt equals 0. It's an integer, but does dt get, dt is here. It actually gets a value at a certain point. It gets dt is the clock dot tick over 60. And when I printed out dt, because I can just sort of like at the end of this, well, actually I can print it to the window now. I can do print dt, right, and it'll give us some number. That number in some way, well, it says it here, dt is delta time in seconds, so it's a change in time in seconds since the last frame, used for the frame rate independent physics. Its unit is in seconds. So yeah, I presume before this divided by, maybe that was in milliseconds before, and now it's in seconds. But it's a tie. I'm just assuming that this well, I should assume this documentation is correct. It's a time in seconds since the last frame. So if it's 0.01, it means 0.01 of a second. So there's 100 of them in a second, because 0.01 times 100 is 1 second, makes that 1 second to be 100 frames in last second. So it's a time since the last frame, basically. So that's what it is, and I'm going to keep all of this here because that's kind of like useful to have as a, that came from the documentation. We're hoping that that's correct. I'm taking on faith that is correct. And yeah, let's continue then. So I want to get all of this in here, and so I need to get this delta time bit in here as well. So here we're going to have to pass in dt, and that is an int. I think it's an int. I'll be careful about that. Float, because it was 0, but actually it's something divided by 1,000, so it's unlikely to be an integer actually. So it's probably a float, and that would be it. So now going back to this thing here, because we're going to basically replace it and remove it, we called it, was it called player pos? Yeah, player pos, right? And then it needs to take in, I wasn't player pos, sorry, take that back, user position, right? And it takes in the player pos, and then it takes in this dt, basically, right? Whatever dt is, right? It starts off with being 0 at the top, and then after one run through, go through. I've got this font here initialized, so I will actually make this font bit bigger in wherever that was where we did the writing thing. So we've got the bigger writing now. Okay, there we go. Just so that is used. I don't like unused variables. Why have it here if you're not going to use it, if that makes sense? So either delete it or don't have it, something. Somebody said their best part of coding is deleting lines of code. And like, I think I'm okay, but I can be Ebenezer Scrooge with keeping code. What I tend to do is put all my junk at the bottom, or out of the way, but never really delete it, because then you can come back and refer to it afterwards. So yeah, there's a whole bunch of that stuff. Now let's just go back. User position. So we haven't got any description on what it is, like in terms of the position of the users is what it says. Lets us move the user around. I need to go and like comment that properly. But I believe now it's got everything that it needs to. Does it need to return anything is the question. Pos X, telephone ringing, I will ignore that. I'm just wondering if it needs to return back player pos, for example, because player pos has been incremented. So should it return it back or not? What I will do is I'm going to comment out this code. It'll be easy to investigate anyway, because if I comment this code out and try and run it, we'll be able to see if it runs or not. So I'll hit F5 to run it, and I'll try and move this thing around, and it still moves. So I didn't need to return anything back. It looks like it's all fine for that. So I can close and we gracefully exit out. And even more so now, we don't need any of this code in here. So now we can see that our code, or our main game loop, is getting smaller and smaller. Yeah, okay. I'm just wondering if I should do something there. Like, it's important. Well, I don't know if it's important, but it's damn helpful to make it smaller and smaller. One reason why is because you want to see where you're putting things, and that's the other reason for exporting the code to all the other places, because you can jump around the code, but you kind of like want to get to, what we've called here, like this function, the game. I'm going to amend it to the simulation. The simulation. Copy that, because then somewhere here it's going to be incorrect, and paste it as simulate. So it's relatively simple, right? I don't even need this return statement, right? The main loop runs and it goes straight to the simulation. I try and keep as literally as absolute minimal as possible in the main loop, because I just want to know where it starts, and that's at the beginning of the code. So now, like, you've got your imports, which are your like stand. Well, actually, really, I should actually even organize this, because the pygame. So these are it's no longer a basic game. Well, it's showing the basic game loop. We're using the basic game loop, but now we're not doing it anymore. That's not the case. So we've got import random. These are our built-in modules, right? And here these are our imported modules. Now this happens to be a very important one because it's all about pygame. We're using the pygame module. But these are our built-in ones, and we might have user-defined modules afterwards as well. So we might go here, right? And I might want to put a whole bunch of this stuff at a later point in time in our library. So, you know, wherever it is pygame here, in this physics module, for example, I might want to make a sub-module somewhere in here. Like a nested module, which has a whole bunch of functions like my library, my pygame library or something, my helper library, which in bigger pieces of code I've done. Now at the moment, my technique or my strategy is to dump everything kind of like down at the bottom, and you see that the last line here, and this is kind of like standard boilerplate template, is the main guard. Like it just goes at the bottom, and that means that none of the code is run until this line is hit, and then it goes to the main. So everything is loaded into the module. So now all of the functions are. This is the only way that I know to hoist in Python, because Python runs everything sequentially. So if you want to hoist functions, that means for them to be read before they're called. If you didn't have this name equals main, Python would just read it sequentially, and you'd need to define all of the other things that you're doing, things like this, for example, that moves it around. I'd need to have defined that before it got called. But this way lets me define them in the order of importance that I want them to be defined in. So I deem this to be not so important. So I kind of want it out the way of the code. And I deem the main module to be the most important thing, to be at the top. And I want the main module to call a simulation. And we can see here at the moment that simulation is not the first module, but the second module. So it's kind of like, do I want this game version? Well, I don't want to remove it or delete it, but maybe I should move it towards the end. So as good practice. Maybe I should make like a file, another Python for sort of like dead modules or previously used modules or something like this. It's like a library of good things that we want, of things that are useful, and then a library of kind of like our junk collection, effectively, that we haven't thrown the code away, but we're less likely to use it. So yeah, definitely that. Let me just do on Twitter again. I'll just do one more retweet, I think, just to make sure. Will be I think we'll probably end it in 20 minutes time, because it's quite a long session. Now, so anyway, yeah, I didn't want. I might even move this. So I wonder if I can move the whole thing like this. Actually, that'd be quite nice. X, does that? No, it doesn't move everything, because if you expand it, Control Z. Okay. I was just wondering if I could export everything. Like maybe I can move it like this. No, it doesn't do that. You actually have. I just thought for a minute. But I could remove it or rename it. So in here, I might make a folder just down here. New file. Legacy code.py. There we go. Right, so I'm going to move some things out of the way, which is basically because X imports, like everything there, in fact, is well, I guess I can import pygame. Right, there's some legacy code. So there you go. I can get rid of it now. It's gone from here, and that's a bit cleaner. Ah, so much more refreshing. When someone says deleting code is the best thing, maybe that's true. I like to sort of like because now I've got the main code and it's running a simulation and the simulation's right under it. It's kind of like in the way that I wanted it, and actually like I did want to chunk out a lot of this stuff, but I've got to be careful about that because I need to. If I was to chunk it out in the simulation, then you see this is clutter in the simulation. But it's too small in terms of like I don't really want this function I'm going to say now is already too big. That's my comment. I should not have a function that's more than 30 or 40, 30 lines of code or 20 lines of code. So this function is kind of like too big. So really what I want is kind of like a setup, right? A pygame setup where it does the init. And I wonder if I can do a pygame setup, which is here, because we basically got it here, right? But if I did, I would certainly need to, or at least, what is the best way of doing that? Because you might need a lot in the setup. I don't know. How much do you need in the setup? You need the init. Do you need a width and height? Yes, you kind of like do. You need a screen because you're going to pass that around left, right, and center everywhere if you're doing it in functions. I could put it into a class. But basically, like one way or another, I need to be able to transfer the screen. The screen's the important thing. Everything's being drawn onto it. This clock thing needs to be there. But again, a lot of the stuff works inside of the calculations happen inside the clock. I'm just wondering if there's anything that I could shorten. Over, I've kind of like removed everything. Maybe these I might have to export them to their own functions at some point, like to another function that calls those functions. Pygame draw the circle. Okay, again. This is while running, but that actually, I believe, possibly could go into, because I could take it out, I think. I could copy that and put it right to the screen. Put it right here. Bless me. I could stick it here. Then I'd need to take screen as an argument. That would need to be an argument now. I'm going to do it like this because I know that this is going to be a big thing. But I've basically now been able, so I can move this line of code away because I don't want it there. Because really all of the drawing objects and all the other things need to happen. They're going to happen in this part of the code, right over here. So basically we'll keep the screen.black for now, but basically all the code runs here. Now what was it that I moved? Okay, Control Z. Oh yeah, it was this. So Yeah, I need to. Okay, so I can take this screen out now, but I needed to pass a screen in, so I did that. So let's just get rid of this line then. Delete that. Basic, and I'm going to put a comment here. All the code runs here. Right. So if we're going to draw anything, it now goes here, and then it will select redraw and redraw and redraw. So right, that's where we're at. All the code runs here. So we get these like redraws, and they'll print to the screens, and they'll do their things, and hopefully they'll do them sequentially. Well, not hopefully. We've got to get it in the right order, so that, because we remember that what happens is you draw this black screen, and then you draw an object on it, and then you draw an object on that, and they go in their order. So whichever was drawn last is like on top effectively. So we've got to be careful about that. But that's really it. So yeah, the connected where is it over there? Connected particles equals, wasn't connected particles, it was the update, sorry, the user position now here needed a screen argument in here, like over there, like the first argument is screen, and at the moment it's a screen.any. But what is screen? Screen is this pygame surface that we're passing on, because we want to draw onto the pygame surface. So long as in here we're going to have our args, and you know the main arg is the screen, which is this pygame surface. It's the main pygame screen, right? So it's the surface. Sorry, I meant to put that, copy that over to here. We're type hinting, and that's what our type hint is. It's that, and then there we go. So it kind of like looks like this now, and I wanted to just take this out, but basically what we're passing in here again is, we don't want to repeat code, so I get a little bit nervous I'm repeating code because I don't want to repeat it too much. But anywhere where we do create something that we are going to update to the screen, we are going to have to pass in this screen argument each time. But that's fine passing around, because we know how we're handling our object and what's actually happening. So in a way it's a good thing, because that's the order flow. So we've got a good order flow for a good flow for our code at this point. So we've got that one, and then what else? Okay, player pos. So this argument here. The position of the user on the screen, and then dt is a measure of time. In fact, dt wasn't just, it was a measure of time. Okay, I'll put it in seconds as well. In seconds since the last frame. Well, in fact, here we go. Right, it's this, copy that. It's dt is delta time in seconds since the last frame. We're literally given that, we're told that. And we don't return anything back. We're returning nothing back because there's nothing needed to be returned back. And I think we can run this F5 now just to test it out. And it's all working there, and we can move things around and everything's fine. So it's all good. So we're up to that point. Now, what's next on our agenda? So we've exported loads of things out, and the code is much smaller. I'm still avoiding like the hard bit because I know I've got to get into doing this. You can't be scared of this. You just got to do it. is our main code. It calls our simulation. Our simulation is slimmed down. Oh, it was this bit here, but we'll keep that in here for now. But basically, we need to start doing the physics, and we've got our connected particles, which is a function which operates on all the particles. But at the moment, it's not doing any hefty work, and I need to make it look like ultimately it's got to get this n body stuff in it. So ultimately, it's got to have these kinds of things in it. Where is it? In it, make particles. That's the make particles bit. In fact, the make particles bit is like a whole bunch of random things, and I have to think about this because I have to get it more correct in terms of I don't think this dictionary was horrendous to use, so it wasn't the greatest example. A numpy array is actually probably and I believe that pygame offers this, but a numpy array is probably a much cleaner way of doing it anyway, because I thought it'd be really clever, and the labels of the particles would be like the integer bits, and then I'll pass through this particle object, this particle class. That'll be clever, and I'll do it that way, which is fantastic if you're doing other things, but it for the simulation, it kind of like just accessing the variables became difficult. Whereas if it was a numpy array, I just look at the rows and the column, and just like I wouldn't even do a for loop in a numpy array. I'll do a vectorized process, and that's that super fast process, like super fast, like it'll be 10x faster probably. So like I kind of like killed the simulation speed by trying to be too clever with the way that my objects look. And Python lets you focus on that, but I think I got too clever on it. So it's my time to like dumb down and become more efficient, or dumb down, or become, but not even dumb down, become smarter in a way, because it'll be harder to do. But let's just go to definition here, connected particles. We've got this whole bunch of particles now. I want to link them or something. So we've got these random particles. See, I wonder, for example, and this is the thing, is maybe I can create a whole bunch of particles and store them into a list straight away, into a numpy array, and then kind of like just work with the numpy array. And that means that this connected particles, this numpy array, if I am clever about it, and this is the way to do it for sure, it will come before the while loop, right? So I'll keep it there. It will come here. So I want to create array, and it's not a list anymore. I'm calling it an array, not an numpy list, because they're slow and cumbersome. So create array of particles, right? So here we were just kept on creating this like a random thing and like posting it on the screen, and we got like those little yellow dots going everywhere. But here we're going to create the particles before. They'll have their positions and so forth, so all of that will be defined. But then we can operate on the particles down here, and that's what we're going to have to do if we want to have our simulation working. And without a shadow of a doubt, thinking about it and doing all of this stuff for the past hour or two, and being scared to do it, I believe that that's the right way. So I might leave the chat now, because it's just been going on for a long time. So this live cast thing, it's been going on for a long time, so I might leave it. But that's going to be the next phase, basically. If I'm going to continue this, it needs to be, I need to create a numpy array. So I can actually make a to-do thing to do. Apparently this goes up. Yeah, there you go. Numpy, or, because I don't even know if this is the case, but I did see it somewhere, or pygame array for particles. particles. Now, it's not a case that, like, you know, I wrote bad code or whatever, but Python is good at this. Prototyping. It let me like put something there and get it working. Okay, it doesn't work on this widescreen monitor, but it did work quite nicely on the other thing. But you know, I've got something that's like the beginnings of something, and you can work from that. So it's great for prototyping and building. Now, when we've done that and we discovered that our simulation is far too slow for our computer, you know, we have to start thinking about clever ways of doing something different. You know, what's my clever way of you know, of making this faster. Now, no longer, so it worked when I had 10 particles and it was fine, and I didn't need to optimize and use a NumPy array. I could have just used the Python loop was the Python list was perfectly fine. It was okay bunging it all into a dictionary, and it did enough of the stuff that way. But the minute I put in 100 or 200 particles, it starts at like, well, not 200, but like 300 or 400 particles, it starts to slow down. And my intention is to put in 1,000, and it would never work. So now I have to start thinking about optimization. So what we can say is that this original Embody was the framework, and what I've got here, which is called test pygame, is going to develop into the new version of the Embody. So we're going to create on our to-do list is a create a NumPy or pygame array for the particles, and then in here in the to-do, in the to-do list, we would also have do the interactions, do the but the advantage of this is it's going to be vectorized. I think that's the correct word, which basically you can operate on an array all in one go. So if I wanted to do something like, and this is a thing I do want to do, this something here, where is it, on any one of these examples here, I want to go through the entire list here. So I'm going to go through the entire vector, and all I want to do is increment one value based on two other values in a very systematic way. And that's what Python's built for. It's excellent for that. So it does it in a vectorized way, which means it does it in a super fast way on the entire block all in one go very quickly. And that's the big advantage that we're going to get. A huge advantage. It's like a 10x gain. It might even be more than that, but it's a large gain in terms of computational time. I'm not going to be looking through. And anyway, accessing this, as I said, it was a bit annoying at a certain point. I no longer have to look through self.particles.values, which was of type. Like each one of these gave me a particle class, which was, you know, this particle class here, which looked like that. And then if I wanted to get the position out of it, so I had to break it down into bits of it. This thing's going to be, which is okay because this is actually a dictionary. But what I had is basically a list of dictionaries, and the list part of it, because the list doesn't know what it's going to be, it's not efficient. So we're going to be focusing just on the pieces that we want, basically, in a vectorized format. So I think I'm going to leave it there. That's it. A lot's done. I know what I need to come back to. I need to be able to create an array for the particles. I will also do some testing though, because maybe I can do maybe we could also test for the white horizontal lines, for the annoying white horizontal lines, because we definitely can't have that going on, or it's got to open up on every screen and work. That's not questionable. It would be horrendous if it didn't do that. And we don't know why that came about. I still don't know why that came about. Um, like, put your comments in there if you do know. And I think that's it. So I'm going to end the stream, and yeah, I'll be saying thanks. Like, leave, I don't know, like it, follow the channel, watch the videos, like it, and all the other stuff. That'd be really, really helpful if you do, because it's quite nice to have that, because at some point I can try and grow it. And we'll come back to this if anyone wants to hear more. Embody simulations of galaxy mergers in Python, something I did 25 years ago in Fortran. I actually worked in Fortran quite nicely. Um, we're doing it again in Python, and ultimately I want to collide two universes. That's what I want to do. Um, so let's get one universe working, and then we'll collide the second one. So that's basically it. And nice.